All right, let's look at the Lesson 2 homework. Just a reminder, the key idea we're talking about here, and you can see this in the equation on your formula sheet, we're talking that impulse is another word for, is the same thing as change in momentum. And because the symbol for change in is delta, and change in anything is always final minus initial, then the impulse, the change in momentum, can be calculated by going final momentum minus initial momentum if you happen to know both of those. Pay careful attention to directions. If you notice there's a change in direction where you were going north and now you're going south, or you were going east and now you're going west, or you're going up and now you're going down, make sure you let one way be positive and one way be negative. But the most common one that we use is this. Impulse is mv final minus mv initial. Now that's really the same equation. Since momentum is mass times velocity, then momentum final is mass times velocity final. But we also proved that it equaled force times change in time. And this right here is a very, very useful shortcut, because in one equation we can then use all of the stuff we learned before Christmas about velocity and kinematics and acceleration and all of our forces stuff. It's an equation that contains mass, velocity, force, ma, and time in it. So it's a really useful shortcut because it allows us to combine several steps into one. Having said all that, let's get to the homework. So, number 1 says insert these words into the 4 blanks of the equation. So, let me make this a little bit smaller so it'll fit on the screen. In a collision, an object experiences, well, a force acting for a certain amount of time. And because we have a force acting for a certain amount of time, we're going to have a change in velocity, which is also going to give us a change in momentum or an impulse. It changes the momentum of an object. By the way, I'll even say this explains how rockets work. Rocket engines eject mass out the back, so there is a force applied to that mass, there's a change in momentum, and the rocket then moves forward. We'll talk about that in more detail later. Let's get rid of that little blurb there. Delete. Number 2. What causes and is equal to a change in momentum? Impulse. Okay. By the way, again, if you're going at a constant velocity, that means your momentum isn't changing. That means there's no impulse. An impulse will change an object's momentum. Number 3. Calculate the impulse encountered by. All right, so for impulse, I'm always looking at either finding it by going final momentum minus initial momentum, or finding it by going mass times v final minus mass times v initial, or by going force times time. Here I see a force, I see a time. I'm going to find the impulse by going force times time. It's going to be 1025 times 0.35. I have no idea what the answer is. What was that, Mr. Dueck? 358.7, 359, probably 360, but I'll go 359. And since impulse is a change in momentum, its units are the same as momentum, kilogram meters per second. However, here, since I went force times time, I would probably write the units as Newton seconds. I'd take either, but usually if I've used the force-time equation to find impulse, I write the units as Newton seconds. If I use the mass-velocity equation, I write the units as kilogram meters per second. But I'm not fussy. Oh, forgot to clear the calculator out. Number 4. This also wants an impulse. Okay. Let's see. I have a force. I have a time. Yep, I'm going to use this version of the impulse equation. So it's going to be 20 times 4. I can do that one in my head. 80 kilogram meters per second, or 80 Newton seconds. Number 5. So number 5, they want me to find the impulse. They want me to find the change in momentum. So whenever I see the word impulse or change in momentum, I almost always write that down first. And then I'm going to say, okay, which version am I going to use? You know what? I see a V initial. I see a V final. Ooh, but I see a change in direction. So you can let north be positive and west and south be negative, or vice versa. Most of you would probably let north be positive and south be negative. So it's going to look like this. M V final minus M V initial. The mass is 1200. The final velocity is negative 30 minus the mass is 1200. The initial velocity is positive 20. You don't need to put the positive there, but think it to yourself just so that you catch it. So I get 1200 times negative 30 minus 1200 times 20, and I get negative 60,000. And since I use mass times velocity, I'll write kilogram meters per second, but you could write Newton seconds. Now, if you left it like that, I'd be okay, but negative is south. So if I do a full vector answer with magnitude, 60,000 kilogram meters per second, and direction, I would do that. Number 6. Well, the first thing I looked and noticed with number 6 is I don't like the units, kilometers per hour. I don't see a change in direction, so because of that, I think each one of these is going to be positive. They want me to find the impulse, the change in momentum. So, okay, I'm going to go like this. And because I see a final velocity and an initial velocity, I'm going to go like that. I'm going to be really lazy. I'm going to do the conversion from kilometers per hour to meters per second right in the question. So I'm going to go 1500 bracket 90 divided by 3.6 minus 1500 bracket 55 divided by 3.6. They didn't give me a direction, so I can only give the magnitude, but that's okay. All they asked for was the magnitude anyhow. So 1500 times 90 divided by 3.6 minus 1500 times 55 divided by 3.6. and I get 14,583. I'll call it 14,600. And kilogram meters per second, since I use mass times velocity. But if you wrote Newton seconds, I'd give you full marks. Number 6. Then we go to the next page. Number 7. Ooh, yeah. So, in both cases, it says here, the impulse provided by the boxer's jaw reduces the momentum of the punch. Usually the final velocity of every punch is 0, so typically the boxer's jaw has to absorb all of the momentum. When the boxer moves away, rides with the punch, he extends the time and diminishes the force. If the boxer moves into the glove, the time is reduced and he must withstand a greater force. If the boxer is able to increase the duration of impact 3 times as long, by how much will the force of impact be reduced? So you realize a punch only lasts for a very short time. So a good boxer with is if the punch maybe of impact only lasts 1/10 of a second, even if the boxer can double it or triple it to 0.1 or 0.3 or to 0.2 or 0.3 seconds, that's huge, because if we make the time 3 times as big, oh, let's copy it. And this is what, question number 7. So, if we can make time 3 times as big, time 3 times bigger, F is 3 times smaller. And the worst would be if the boxer moves into the punch, so that would cut the time of impact even shorter. By how much will the force of impact be increased? Well, force will be 2 times larger if time gets half as big, but we still have to absorb all of that impulse. Of course, the real solution is just don't get into a fight in the first place. Oh, here we go. A boxer being hit with a punch contrives to extend the time for best results. That's true. But a karate expert wants to deliver the force in a short time. Isn't there a contradiction here? No, because a boxer wants to reduce the force on their face, but a karate expert wants to maximize the force on the object that they're hitting. So a karate expert wants the force to be as large as possible so that the time of impact is small. A boxer wants the force to be as small as possible, so the boxer wants the time of impact to be large. I hope that explanation just kind of makes sense. I hope. So that's impulse, change in momentum. So I'll email this out on Wednesday, and I'll give you another Whoa Wednesday assignment. Remember, the Whoa Wednesdays are optional, but if you have a missing assignment and you want to replace one of your missing assignments with the Whoa Wednesday assignment, you can. I'm doing that because some of you have told me you don't have printer access, you can't really print up the assignments. I get that. And also, I want to keep your curiosity alive. I know that I'll talk about science in my classroom quite a bit, and I miss having these discussions with all of you. Okay?